Hi everyone, next packet is periodic properties of the elements. Now, in order to kind of understand the true nature of the periodic table, we kind of have to take a journey back in history a little bit. Okay, the periodic table was first invented by Mendeleev back in 1869. Okay, and if you invent the periodic table, you of course have an element named after you, Mendelevium. Okay, which was, I think, 101 or something. There he is. Yeah, there's Mendelevium. Okay, and there's the element named after me. Now, so let's talk a little bit about the periodic table, and then we'll get into the underlying trends that describe it. Okay, so invented by Mendeleev. Okay. 1869. So the year is important, right? Because it's way before the proton, the nucleus, the electron, all things like that. They were discovered in the early 1900s. So a good 40 to 50 years before people started to look what was inside an atom, Mendeleev created the periodic table. And we've already talked about it a little bit. We talked about how he arranged it, right? And he arranged the elements, and his periodic table, there's a picture of it down here. Okay, aside from the transition metals, which kind of should be kind of slightly moved around a little bit, it's pretty much the same order as the periodic table we know today. Okay, and he arranged his elements left to right in order of relative mass. Okay, so the lightest compared to all the others went first, which was hydrogen. The next lightest was helium. Next lightest was lithium. So he was able to kind of order them in order of weight. Okay, so I made like a list, 100 and something elements long in order of weight. Right, that is exactly the same order as atomic number, because as you add a proton, you pretty much add a neutron. Those, so things with a higher atomic number weigh a little bit more than the previous one, if that makes sense. So the same order as we have in the modern periodic table is arrived at just through ordering in terms of weight. Okay, so now yes, atomic number. Back in the day, weight, but it's the same order. Okay, now as I mentioned in the last packet, we mentioned that in the last packet too. Okay, but we also mentioned that Mendeleev put like a return in his ancient periodic table after helium to make lithium appear in column 1, right? Okay, why did he do that? For the second major thing, right? So they're organized in order of weight, but that would be a list, 100 and something elements long. You hit return in the right spot, things line up under each other if they have the same chemistry. Remember that, right? So Mendeleev put in those returns. So elements with similar chemical, physical properties in the same column. And we know this is group chemistry today, right? So group 1 makes +1 ion, we know. Okay, group 1 are alkalis. Okay, group 8 are all inert, right? Okay, so things in the same column have the same chemical and physical properties. So those two simple concepts, if you let them play out, create essentially the modern periodic table. Okay, now Mendeleev's periodic table doesn't look quite like today's, because guess what? Back in the day, they hadn't discovered all the elements. And this is Mendeleev's genius. It's kind of the Swiss cheese approach. So he kind of left gaps for elements that had not yet been discovered. Okay, so left gaps for new elements. And that, in a way, was his genius, because he understood kind of group chemistry. Things in the same column have the same chemistry. Then he understood left to right, so he could kind of predict the weight of something. So he had a hole in his chart, and he said, hey, take for example germanium. Now germanium today is known as, today it's known as germanium. Back in the day, Mendeleev called it ecosilicon, right? Okay, so based on its location in his periodic table, and this is a thing that hadn't been found yet, right? He predicted its mass, 72, its actual mass, 72.6, right? He predicted its density. He predicted its formula. Alright, so he got all those exactly right. It's like he's got some magic crystal ball. Well, not really. He just understands trends in the periodic table. Okay, so Mendeleev's genius, he was able to leave gaps in his Swiss cheese periodic table And later, yeah, people filled in the gaps with elements which were discovered later. So that's kind of smart. Okay, so we recall that the chemistry of the elements, if we remember our kind of a couple of packets ago, we remember our battleship analogy, right? So it's those valence electron structures essentially which led to similar chemistry. Everything in the same column had the same chemistry, yeah, fair enough. But that chemistry varied what we call periodically. So if I kind of go across any row, if you think about it, I sample row 1, 2, 3, 4, 5, 6, 7, 8 as I go across, right? And this is periodicity because the periodic table swings like a pendulum, has periodic behavior, right? So metals on the left, non-metals on the right, okay? That's where the name periodic table comes from. It's because the rows are periods, they swing from left to right, metal to non-metal. And the properties swing from left to right, metal to non-metal. So they're good conductors on the left, insulators on the right, metals on the left, non-metals on the right, that kind of thing. Okay, but underlying all that, that gradual change in chemistry is that gradual change in electron configuration. Okay, we add one more electron to the valence layer as we go across, right? Okay, so popping the hood then. So we pop the hood on what's really leading to these periodic trends, right? It's the electronic structures. So we're going to look in detail at certain trends in the periodic table, and all trends in the periodic table, as we'll speak about in a moment, are bottom left to top right. Okay, and we've seen one already, which was electronegativity. Okay, so the layout of the periodic table is directly correlated to elements' electronic structure, as we saw that with the dot diagram periodic table. Okay, and it was kind of reinforced just in the last packet with, you know, the construction of the periodic table based on, you know, 1s2, 2s2, all that business, right? Okay, so we can look at additional chemical and physical trends, right, which are again bottom left to top right based on electronic structure. Okay, now as it says down here, all trends in the periodic table are bottom left to top right, more or less, right? We've seen one already. That was electronegativity. If you remember, the weakest, the Pee Wee Herman of the periodic table was francium down here, and electronegativity at 0.7. Then it was a diagonal trend, low to high. Highest was fluorine. Electronegativity is really defined as electron stealing strength when bonded. Okay, so fluorine's an electron stealer. Metals, which are on the left here, are weak. They're electron donors. Okay, weak and strong makes an ionic bond. Two strongs makes a covalent bond. Okay, shared electrons if we have two atoms from the top right. Stolen, ionic bond, left and right. Okay, so got it here. So which bottom left, top right trend have we already encountered? Electronegativity. Let's call it EN from now on, right? Because I don't like to write the big word. Okay, question. And it's an interesting question, right? Is it real? Is electronegativity real? In other words, is it something you can actually measure? Can I get a special probe, stick it into an atom, and find out its electronegativity? The answer is no. It has just, the numbers are just too clean if you think about it. It runs from 0 theoretically for no electronegativity. Lowest is actually 0.7, but it runs from 0.7 up to 4.0, right? That's not an accident. You don't measure something to fall on a 0 to 4.0 scale. It's not like a grade, right? It's like elements have a grade average. No. Electronegativity is actually calculated, okay? And it's calculated from a number of things, primarily the things we're going to look at, okay? So electronegativity itself is an equation, and the equation was originally developed by Linus Pauling, a very, very famous chemist from the 1960s and 70s, who actually was a professor at the University of Chicago. Okay, so that's kind of cool. All right, so electronegativity is actually pops out of an equation which features other bottom left to top right trends, namely the radius or the size of an atom, the ionization energy, which is, you know, how much energy it costs to pull an electron out of there, and electron affinity, electron kind of attractiveness, if that makes sense. Okay, so we have these three trends, or three properties, which go into, as variables, the electronegativity equation. There are several kind of versions of that equation now, but Linus Pauling's is the most famous, I guess. He was the original. And it turns out that my father-in-law actually went to the University of Chicago in the 1960s, and he actually went to lunch with Linus Pauling, which was kind of cool. And he reminds me of this every Thanksgiving. Okay, well, that's okay. I like the story. All right, now, so We'll look at these various trends and see kind of where they come from. Okay, so just as a reminder, there's our electronegativity trend. Okay, remember the electronegativity trend runs low to high, bottom left to top right, and that kind of borderline there separates metals low from non-metals high electronegativity. Okay, and remember, it's not a pure atomic property. It's not something you can measure. It's something you calculate from the other things we just showed you. Okay, now when it comes down to it, there are some very simple concepts which underpin all of those trends. Okay, be it size, be it affinity, be it ionization energy, right? So there are some very simple properties, and we think just out loud a little bit about, well, you know, what would affect how strongly the nucleus holds onto its electrons, right? So if you think about it, the nucleus, if it holds onto its electrons, it's going to be hard to get them out. If it holds more weakly, it's going to be easier to get out, and that will lead to electronegativity strength, right? Okay, so the first one, very simple. What atomic scale factors do you think affect how strongly the nucleus pulls on its orbiting electrons? And then that kind of concept will kind of bleed over into the trends, right? Okay, so think about, nice way to think about this is, so the nucleus holds onto its electrons a bit like the Earth holds onto its satellites, right? So electrons, you know, they're orbiting around an attractive center, plus and minus, whereas satellites, masses, right, they're orbiting around an attractive planet, if you like. Okay, the first one is the size of the planet, right? Jupiter has like hundreds of moons or something, right? Because it's really big, right? So the bigger you are, the more satellites you have, right? That's true with atoms too, right? The bigger the nucleus, the more pluses, the more minuses, yeah? So the more attractive the nucleus. So the nucleus is more attractive, the more plus charges it has. So the charge on the nucleus is like a big deal, right? The stronger the nuclear charge, the more strong the electrons are held there. That's an obvious and simple thing, isn't it, right? So very simple, more positive equals more attractive. There's a simple kind of concept, right? Okay, so if you like, the pull is proportional to Z, the atomic number. Okay, all right. It's like gravity. The bigger the planet, the more gravity it has. The more protons the nucleus has, the more it pulls on those electrons, because it's plus minus attraction. Okay, so that's the big one, right? So the more protons you have, the more attractive the nucleus is, the stronger it holds onto its electrons. All right. Next one, think about it, right? So if you put a satellite in orbit, it doesn't matter how big the planet is, it will eventually, as it gets further and further away, eventually get further and further away, and eventually not feel the effect of gravity and just drift off, right? Okay, so distance of the electron from the nucleus is a factor, right? Now it drops, the attractiveness drops off pretty quickly. That's called the inverse square law, and it works for gravity, works for physics with charges too. Okay, so you double the distance the electron is from the nucleus, it quarters, it's inverse square, it quarters the attractiveness, right? So distance of electron from nucleus, that's the next one. That definitely affects how strongly the electron's held, right? So one, the charge of the nucleus. If it's a lot of protons, it's held more strongly. If it's less, it's held more weakly. That's small planet versus big planet. And then distance, right? Distance from the nucleus, right? Or distance from the planet, right? As you go further out into space, the gravitational pull of the Earth falls away. As you go further out from the nucleus, so does the attractive plus charge, the electric field, right? Okay, so distance from nucleus, pull is proportional to 1 over distance squared, it turns out. It's an inverse square law. It drops off really quick, right? Okay, so further away, if you like, equals weaker, or closer equals stronger. It's a simple concept. Okay, now the next one is a weird one. Okay, the next one's a weird one. Okay, it's called shielding. And before we go any further, all these combine to what's called the effective nuclear charge, right? So the effective nuclear charge, ZEFF, is like, it's like a tax rate, right? So if I have an effective nuclear charge of 5 and the nucleus is a charge 10, it's a 50% tax rate, right? So the further out you go, the higher the tax rate, that kind of thing, right? So electrons don't necessarily feel the entire nuclear charge. If they're further away, they feel less, so they've kind of been taxed, if that makes sense, okay? And one thing that leads to taxation is shielding, okay? Now, we'll do this in more detail on the next page, but if you think about this, right, so think about lithium, right? Now, I'm going to do a mixed model, right? So here's my 1s orbital with 2 electrons in it, yeah? 1, 2. And there's my valence electron out there, right? Lithium has a +3 nucleus, right? You'd think that electron feels the attractiveness of a +3, but it doesn't, because if you look at it, there's 2 in the way. It's like it's peering through this fog of negative charge, right? So the effective nuclear charge equals the real charge minus the shielding, right? So what does that mean? The attractiveness that one feels, which is the effective nuclear charge, equals the charge on the nucleus +3 minus what we call shielding electrons, electrons that are in the way, and they're in the underneath core levels, right? So the number of core electrons in the way shields the nucleus, right? And that's 2. So it actually feels the effective nuclear charge of +1, even though it's a +3 nucleus. Now that's very, very important. That shielding concept really comes into play as we go across rows, okay? And really does underpin electronegativity, okay? So bottom line is core electrons shield or screen, shield the nucleus from valence electrons. So the pull is proportional to Z plus the tax rate, if that makes sense. Okay, so the effective nuclear charge, the pull, equals kind of the equals your gross pay minus the taxes, right? So the shielding electrons kind of cut off some fraction of the attractiveness because they're shielding the nucleus. It's a weird concept, but it's, you know, a real concept. Okay. Now, that whole shielding thing is shown in more detail on the next page, right? Okay. So it turns out that effective nuclear charge really is, if you remember your Wizard of Oz, the man behind the curtain. It's the thing that controls virtually everything. And as we do some pictures in a moment, you'll see that. Okay. So the effective nuclear charge really is what determines the value of these various properties we're going to look at, right? Okay. And effective nuclear charge, it's got 3 things going on. It's got the actual size of the nucleus, if you like, the gross pay, the number of protons. Then it's got the distance, which is like a taxation effect. The further out those electrons are, the less they fill that nucleus. And then we've got the screening effect, which is another form of tax. so nuclear charge is kind of taxed twice, right? It's taxed on distance and it's taxed on screening. Okay. So here's that nicer version of lithium, right? So this is well, it's kind of a generic, right? So here's the nucleus. It is actually lithium, right? So here's my 2 electrons in the way. There's my valence, and it talks about the effective nuclear charge is the nuclear charge minus the screening electrons, just like we showed you here. Okay, we'll do actual calculations in a little bit more detail later, but that's the concept. Okay, now. Here's one. So actually, here's lithium, right? So here's lithium in a little bit more detail. All right. So lithium has that +3 nucleus. There's the 1s2, if you like, you can do that. There's 2 electrons in the way. There's the valence electron. So 3 minus 2 in the way equals an effective nuclear charge of 1. Okay. So we can do that again down here. This is lithium. So the effective nuclear charge is 3, which is the nucleus, minus the 2 in the way, equals +1. Now, let's look at fluorine. Fluorine, as you know, is super electronegative. It's super attractive. That means it has a higher effective nuclear charge. Things that are highly electronegative, electron stealers, will necessarily have a higher effective nuclear charge. Things that are low in electronegativity, like lithium, have a low, it can't get much lower than 1, right? Have a low effective nuclear charge. So let's do the fluorine. There's a nice little picture of fluorine, but I prefer to do my kind of mixed one, right? So fluorine has a +9 nucleus, right? And then we have 2 on the inside, right? So we have that 2 electrons there, right? And then we have 7 on the outside. Now this is a bit like, we'll come back to this concept later. These electrons in layer 2, so fluorine, row 2, column 7, right? So 7 on the outside, 2 layers. When these guys look in, they're a bit like a ring of horses on a carousel or something, right? If you remember, like a trip to the carnival or fairground, right? Okay. So when they look in, they don't see each other because the others are off to the side, right? And they look in, all they see when they look to the nucleus is 2 in the way. So what's the effective nuclear charge? Well, it's 9, right, which is the center charge, 9 protons in fluorine, right? And these 7 electrons see these 2 in the way, right? So 9 minus 2 equals 7. So fluorine has an effective nuclear charge of plus 7. It's like a planet that's 7 times bigger than the lithium planet, if that makes sense. So obviously that's much more attractive to electrons than this. Most electronegative element, one of the least, okay? It turns out that the effective nuclear charge is the same as the column number, which is interesting. So column 1, the effective nuclear charge always works out to 1, column 2, 2, etc., right? Okay. So the effective nuclear charge increases across every row in the periodic table, which is kind of interesting. All right, so fact, as the atomic number increases across a row, the effective shielding stays constant, right? So if you think about it, when you go across a row, you're just adding electrons to the valence layer, right? Layer 2, lithium has 1 in the valence, all the way at the end, neon has 8. So you're just adding electrons to the valence layer, and they're not affecting each other in terms of screening. It's just those core electrons that are in the way, and that's constant, right? That's that first layer full all the way across, right? So as we go across a row, the shielding stays constant, but the effective nuclear charge increases by 1 every time we go across an element because the nuclear charge increases by 1, okay? All right, so effective nuclear charge increases across every row in the periodic table. That's a given fact, okay? So fixed amount of screening across the row, same number of full layers, but increased nuclear charge, okay? All right, so that's the man behind the curtain, effective nuclear charge, right? Okay. Now, there's a graph, right? There's a graph. Now, I kind of lied to you just a little bit, right? Okay. I said the effective nuclear charge is the same in every column. And if you do the math, it's true. If you worked out the effective nuclear charge of chlorine, you'd get plus 7. If you worked out the effective nuclear charge of sodium, you get plus 1. So with the simple math, group 1, this is chemistry 101 level, right? Group 1 plus 1 effective nuclear charge, group 2 plus 2 effective nuclear charge, and it's the same for every column. Okay, so you think, oh, it's fixed, right? And then I'll show you the graph, and it just slightly, there's one at the end of the row, right? So it's not level. If it was level, it would be true, right? But it's a slight drift up. It's a slight drift up, right? Okay, so the effective nuclear charge, and this is a little bit beyond the course, right? Okay, the effective nuclear charge as you go down the column actually ticks up just a little bit. So it's like starts at 1, maybe it's like 1.5 at the bottom or something. So interesting. So the question is, that really subtle but important trend, why is that true? Okay, and I can tell you with this picture. Okay, now take this order. It's just a story from when I was younger, right? So when I was younger, I actually went to school in Chicago, right? I went to UIC, and I lived close to Halstead Street, aka Boys Town, right? And I used to go, because it's really kind of interesting, I used to go to the kind of gay pride parade every year, because it's kind of a big thing in our neighborhood, right? And when you go to the gay pride parade, and if you haven't ever been, I recommend it. Okay, like myself, I'm not gay, but it's really a good time, right? So you go, and it's, you know, lots of good interesting stuff going on. You kind of see guys like this walking around, right? So this guy is wearing a mesh shirt. Right? And this reminds me, believe it or not, this reminds me of why the effective nuclear charge kind of slightly grows. Now think about it, right? If the atom's really big and those screening electrons are kind of filling that space, they're spread out more, right? So they're less dense, they're thinly spaced, right? They're more thin, if you like, right? So if the cloud's kind of thinner, it's kind of easier to see through. And if I'm peeking through the cloud that's thinner, I actually see more of the nucleus, right? So for the lower elements, when the screening electrons are further from the nucleus, it turns from a solid shirt into a mesh shirt, if that makes sense. It's easier for valence electrons to see through the nucleus, so they actually feel a little bit more of its power. So that's why there's a slight tick up in the effective nuclear charge when you actually go down the column. But that, again, is something that's not really tested in 101. But if you ever saw that graph's in 101, you're saying to yourself, well, why aren't they all level, right? Why do they actually tick up just a little bit? It's because of the mesh shirt effect. Weird, I know, but that's it. Okay. Now, so that's the man behind the curtain. Okay, that's the man behind the curtain, which is effective nuclear charge. And as we'll see when we look at the stated trends, the radius and the electronegativity and things like that, right? That's what's really driving it. Okay, so well, I'm a couple of minutes away from the timer going off. So what I'm going to do, start and stop again real quick. Okay, so I'll see you in a second. Okay, so the first trend we're going to look at is atomic radius. Now, remember, trends are always diagonal, right? If I remember, I showed you my first slide, one of my first slides, bottom left to top right. Now, they're always diagonal. The question is, well, who's high and who's low? One of them is switched. The highest number is down here and the lowest is up here, and it's actually the first one, which is radius. Okay, the rest of them are low to high, bottom left to top right, but radius is switched. It's still bottom left to top right, it's just the order is switched. Okay, so let's just talk about that. All right, now, what I want you guys to do, get a piece of paper, all right, and we kind of use it as an aid, right? Okay, so what I'm going to do is get lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, right? And I'll kind of, you've seen this before, right? And then lithium, sodium, and I'm not going to draw all the electrons. They just get, more and more big, right? So all the way down here. This is cesium or something down here, right? Okay. So, question is this. Put this to the side for a second, right? Question is this: how do trends in radius or size of atoms vary across a row and down a column? Then we combine those trends to make the diagonal, right? So a diagonal is a combination of horizontal and vertical, isn't it, right? So let's think common sense. How do the size of atoms change across a row and down a column? The easiest one is down a column, right? Do they get bigger or smaller as you go down? Well, obviously they get bigger because you're adding a layer each time, right? So down, they get larger. Okay, so we'll actually do the second part first. Down a column, atoms always increase in radius. Down a column, adding shells. So it's real simple. Every time you go down one, you add a layer, right? So they're going to get bigger. All right. Okay. So that's simple, right? So down any column, atoms get bigger, and that's true for any column in the periodic table, because every time you go down one, you add a layer. Obviously, it's bigger. Okay. Now, across a row, interesting. We kind of mentioned it already, right? Now, here's your concept, right? So, common sense. What does common sense say? As I go across the row, I just keep, I keep adding electrons to atoms, right? I add a proton, I add an electron, yeah? So do atoms get bigger as I go across, or do they get smaller? I'm adding more electrons, right? And you think to yourself, well, electrons need more space, perhaps they get bigger, all right? That's actually incorrect, right? Okay, because they're actually going into the same orbit, right? So it's like those horses on the carousel I talked about at the carnival. It doesn't matter how many people are sitting on horses in that outer layer, the layer doesn't move, right? So it's a fixed distance from the nucleus. That's the theory of it, right? But wait a minute, what about the man behind the curtain? The effective nuclear charge on lithium has a +3 nucleus with 2 in the way, +1 effective nuclear charge, right? If I go all the way up to neon, all right, group A, it's going to be +8, right? Neon is a +10 nucleus, right? 10, and again there's 2 in the way, which equals +8. So as we go across, mentioned it already, the effective nuclear charge increases. The pull on the electrons from the nucleus increases across the row. What effect does that have? Well, think about it. It pulls them in just a little bit. So actually we get a slight contraction across every single row, because as the effective nuclear charge increases, the pull on the electrons increases and they just tighten up just a little bit. So it's very slight, but it's true for every row. Atoms shrink slightly as you go across every row because of the increase in the effective nuclear charge. So across every row, effective nuclear charge increases across the row. Therefore, orbiting electrons attracted more strongly. Therefore, contraction. The valence layer contracts just a shade. Okay, so if you go back to our picture, they get bigger going down and they get smaller going across. So let's think to ourselves, where's the biggest atom in nature, left or right? Well, it's going to be left because they get smaller that way, so they get bigger that way. Where's the biggest, top or bottom? Well, at the bottom. So the biggest atom in nature is bottom left. Francium and cesium are the biggest atoms in nature. Where's the smallest? Well, it's going to be top, because there's less layers, and it's going to be right because of the contraction. You may be saying to yourself, well, it's going to be neon. Well, no, it's not. It's actually an atomic trend. It's going to be helium. So helium's the smallest, top right. Cesium, francium are the biggest, bottom left. Okay, so that's the trend. Large to small for radius. Okay, so it's reversed from electronegativity. It's an inverse of that. So the largest atom is bottom left. The smallest is top right. Okay. All right. There's a picture, right? So there's a picture. That's a little busy. This is atomic number versus radius. And you can see this is like a period, right? This is a row in the periodic table. They kind of decline across. A better one to look at is my trend, right? So that was my picture here. It's just got numbers on it, right? So as you go down, they get bigger. As you go across, they get smaller. All right. Okay, and here's the whole periodic table. So every column they get bigger, and every time across they get smaller. Now you're looking at that. There is a typo. Do you see it? It's nitrogen. Here, nitrogen is 70, right? It's out of trend. It's actually 75. It's correct here. Okay, so be careful of that. It is a true trend. It's an absolutely correct trend for every row and column in the periodic table. Okay, size. Okay, anything lower down in a column is bigger. Anything further right in the row is smaller. Okay, now with that in mind, we can answer some kind of simple descriptive questions. This is nice for a test because it's descriptive chemistry, right? Okay, descriptive chemistry is a trend essentially, right? So here's the question. Arrange the following atoms in order of increasing atomic radius. Okay, now they've given us sodium, beryllium, and magnesium. Now, for an easy question to start, I've picked atoms that are close together, right? But it doesn't matter where they exactly are. There they are, right? They could be separated further. They could be higher, lower. It's their relative position. Who's up, who's down, who's left, who's right, because it's all about making a diagonal line, right? So what I like to do, I like to get the atoms themselves and make like a mini map of where they are in the periodic table relative to each other, right? Okay. It looks like that, yeah? And then I say to myself, well, once I've got their relative positions, the diagonal line defines trends, right? So I'm going to draw a diagonal line. Then if I remember, well, radius, that's the largest and that's the smallest, right? So whoever's bottom left is the biggest, whoever's top right is the smallest, and it's where they fall on that diagonal that defines their position, bottom left to top right. Okay, so now read the question. Be careful, right? Because students often switch it. It says arrange in order of increasing. Increasing means what? Small to large. Who's the smallest? Top right, beryllium. Okay, I like to do bookends, right? Who's at the other end of the thing? Who's the bottom left? Well, it's sodium. Who's in the middle? Magnesium. That's the order. Ah, makes sense? Makes sense. Okay. Now, next one, ionization. So these radius, ionization, and affinity go into the equation for electronegativity, right? Okay. And again, they all have bottom left to top right trends. It's just a question of who's big and who's small in which position. The only one that's different is radius. We just did it, okay. The rest of them are just like electronegativity. Biggest value, top right, smallest value, bottom left. Let's look at it. All right. So what is ionization? What is ionization energy, or precisely first ionization, right? Ionization is that process of removing an electron from an atom. And we always talk about making a positive ion, right? Because you can get a machine to do it. So real quick, if I had a metal plate and a metal plate, and I put a giant voltage across there, right? I could put some atoms in there, yeah? And if I just kept turning that voltage up, yeah, the plus side will eventually rip electrons off those atoms, right? And the energy needed to remove one electron from each atom is called the first ionization energy, and it's measured in kilojoules per mole, right? So how many kilojoules do I need to remove a mole of electrons from a mole of atoms, right? And that's what we see down here. And they have to be in the gas phase, all right? Now, so that's sodium, right? So if I have a sodium atom, I wrench an electron off it, I get a sodium plus, and the electron's just pulled away, right? And that's a low number, actually. That only costs, I say only, you'll see some bigger numbers in a minute, that only costs 496 kilojoules per mole, right? Now, if you think about it, sodium's element number 11, so I could pull out, if I just kept turning up the voltage, I could pull out 11 electrons if I just kept ramping it up, right? I could do that. However, we're only interested in apples to apples comparisons, so we only look at what's called first ionization. Now think about that. That's how much it costs to get one electron, right? Why is that important? Because everything has at least one electron. Hydrogen has only one electron, right? So it only has a first ionization. Helium has two, so it has a first and a second. Lithium has three, so first, second, and third. If we want to compare, we've got to compare first ionization because everybody has one electron at least, right? Okay, so let's draw a picture. Let's draw a picture. So sodium, and you can kind of see why it says a small number, right? So sodium is element number 11. So if you like, and you'll see why group 1, we did lithium a little bit ago, right? Had an effective nuclear charge of +1, and I said, hey, whatever column you're in, that's your effective nuclear charge. Look at this. Sodium's element number 11, right? So the effective nuclear charge is the nuclear charge 11, and there's 2 layers in the way, getting in the way of this valence, right? So that's 10 electrons. So it's got a +1 effective nuclear charge. But that electron's in the 3rd layer, so it's further out, right? So it's slightly less strongly held. So it's really easy to remove. It's really easy to remove, okay? And what do we get? Well, we turn into Na, still +11 nucleus, right? With 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I removed 1. That's my sodium +1 ion plus an electron. Now think about it for a second. If I tried to pull one of these electrons out of what's left, the sodium +1 ion, think about that. That's going to be much, much harder. And this kind of tells you why the full outer layer is super stable, right? Because I've got this +11 nucleus, yeah? And now the valence layer is the full outer layer, right? It's just been kind of removed. So this is now the valence layer, right? It was core, now it's valence. And there's only 2 in the way. +9. So the +1 sodium ion has an effective nuclear charge of +9, so it's virtually impossible to get electrons out of there by natural means because it's a super high effective nuclear charge. It makes that stable. So if you ever wondered why things are stable with full octets, the effective nuclear charge is off the charts. Okay. Alright, so that's isoelectronic with neon. Okay. So that kind of explains why full valence layers are stable. Alright. The electrons are being held really tightly, hard to get them out. Okay. Alright. Now, next one. How do you think radius effects and effective nuclear charge effects, in other words, up and down is the radius thing and across is the effective nuclear charge thing, right? How do you think effective nuclear charge and radius affect ionization, right? Well, let's look at our little map again. Right? As I mentioned, for all intents, move this down, right? For all intents and purposes, right, in Chemistry 101, things in the same column have the same effective nuclear charge. Group 1 has a +1 effective nuclear charge. We just saw that for sodium and lithium atoms, right? Okay. But when we have valence electrons which are further from the nucleus, hey, inverse square law, the further the electron is from the center, the less strongly it's held. So as I go down a column, valence electrons, although held by the same effective nuclear charge, are further from the center. So that means they're less strongly held. If they're less strongly held, they're more easily removed, so the first ionization goes down. So down a column, the first ionization will decrease because valence electrons are easy to remove because they're further from the nucleus. Alright, so decreases top to bottom due to increased distance from nucleus. Now put in brackets, effective nuclear charge is constant, right? So they're being held with the same effective nuclear charge, but they're further away. It's like those satellites in the higher orbits are kind of easily more floating off into space, right? Okay. So as we go down the column, first ionization decreases. So if I go back to my kind of all-in-one chart here, let's talk about first ionization. So this is low first ionization towards the bottom because the electrons are further out, right? Okay. As we go down, first ionization decreases. What about across the row? Well, as we said, across the row, the radius is essentially the same. It squishes down a little bit, which actually holds onto the electrons just a little bit stronger. It's kind of the reverse effect. But the 600-pound gorilla in the room is what? It's effective nuclear charge. You go across rows, effective nuclear charge gets bigger and bigger and bigger, so the electrons are more and more tightly held, right? So first ionization energy increases across every row because the effective nuclear charge keeps going up. Okay, so across a row, we get high first ionization energy. So the highest is to the right, the lowest is to the left. Okay, let's write that down. So across the row, increases left to right as effective nuclear charge increases. Okay, fair enough. Okay, so that means in the big scheme of things, as we go across, first ionization increases. As we go down, first ionization decreases. So where's the smallest value? Well, it's going to be to the left and at the bottom, lowest. Where's the highest? At the top to the right. This is an atomic trend, so helium's included. Helium has the highest first ionization energy. Cesium, francium, bottom left have the lowest. It's the same trend, bottom left to top right, as electronegativity. But, you know, it's just defined differently. Okay. If we look at the map, so there's a map of first ionization energies. As you can see, lowest down here, highest up here follows that classic bottom left to top right trend. Now, here's some really interesting stuff. Now, I was asked this, and it's a standard question on any kind of higher level chemistry test, right? I was asked this on the first day of getting to graduate school on the placement test, right? Okay. If you look, nitrogen is either higher than it should be or oxygen is lower than it should be, right? The trend should be increasing. So oxygen's too low or nitrogen's too high. Similarly, boron's too low or beryllium's too high, right? So we have these odd pairs, right? We have these odd pairs, beryllium, boron, nitrogen, oxygen pairs, right? Why is there kind of a kink in the graph right there? Well, it comes down to some very subtle details in electronic structure, right? Okay, so generally speaking, we have a bottom left to top right trend, but there's something going on with beryllium, boron, nitrogen, oxygen. Let's take a peek, right? So, subtle trends in first ionization. So why are those special peaks there between beryllium and boron? So they're kind of out of sync, right? And oxygen and nitrogen, they're kind of out of sync. It's almost like they've been reversed, right? Okay. Let's draw some ground state electronic configurations, right? So where are the electrons in these things? So beryllium, element number 4. 1, 2, 3, 4. Right? Boron, 5. 1, 2, 3, 4, 5. Look what we got here, right? We've got what's called subshell screening, right? In boron, I've got my 1s that's full, so that's 2 electrons in the way, and I've got my 2s that's full, and then I've got my p electron up there. So boron is element number 5, right? All right, so its effective nuclear charge is 5, which is its nuclear charge, and there's 4 in the way equals +1. Right, so that p electron, p's are a little bit further out, remember, essentially sees 4 electrons in the way, effective nuclear charge of +1, right? Beryllium, well, it's got a nuclear charge of 4, right? Okay, so it's got a +4 nucleus. Then it's got my 1s, there's 2 in there, and then the 2 electrons here are valence, right? So those 2 see a nuclear charge of 4 and 2 in the way is +2. So it turns out beryllium, even though it's further to the left, it should be lower. It's actually a little higher because of this, what we call subshell screening. Those s electrons fill first, so they're a little closer. There we go. So that explains why boron is a little lower and beryllium's a little higher, because boron has a +1 effective nuclear charge, whereas beryllium only actually has a higher one at +2. Okay, so that explains that. So if you ever see beryllium and boron in a question, switch them. Right. It's a little bit, well, it's similar but different. Okay, so if you look at nitrogen and oxygen, let's do the same thing, right? So nitrogen element number 7, 1, 2, 3, 4, 5, 6, 7, and we saw this effect when we looked at Hund's rule. Remember Hund's rule? Okay, oxygen 8, 1, 2, 3, 4, 5, 6, 7, 8. Now, nitrogen has what we call half subshell stability. Yeah? If you have 3 electrons, right, there's kind of 1 in each of the 3 p lobes. Yeah. But when I have oxygen, one of the lobes has 2 electrons in it. Yeah. And those 2 electrons are spin paired, so it took a little bit more force to get that second electron into the lobe because it's occupying a space with an electron already in it. If it costs me energy to get it in, it's easier to get out, right? So that's what we call half shell stability. We say this is more stable, this is less stable because that one is easier to remove, lower ionization. Okay, so oxygen's a tad lower because of the electron-electron repulsion in that first doubly occupied p orbital, right? So for all intents and purposes, you just, you can think about this in detail, or you can just remember, hey, if I ever get one of those trend questions with beryllium and boron, switch them. If I ever get one of those trend questions with oxygen, nitrogen, and it's a first ionization question, switch them. Okay. Oh, I think I had a bit of a I think I was talking to a camera that was switched off for a second there, but hopefully you could hear me, and hopefully you saw on the paper here what I was doing. Okay, all right. So bottom line is, look at the key there. Removing electrons from full or half full is harder, so it's kind of glass half full, glass empty, than over here. Okay, so they call that half subshell. You can say that's more stable, that's less stable. I like to think about that's easy to remove, or if you like, that's harder. Okay. All right, so here's a question, right? So using only the periodic table as a guide, in other words, you're going to put them in a diagonal relationship, right? List the following atoms in order of increasing first ionization. So remember my hint, right? Put them in a little map. Okay, so I got lithium, sodium. So lithium is always above sodium, right? And it's a relative position. Yeah, they're not close like the last example. They're a bit spread out. And then we got oxygen and nitrogen. So nitrogen is here and oxygen is here, right? Now, well, good enough, right? So there's my trend, right? I know that the lowest is here and the highest is here for first ionization, okay? And then I do my diagonal lines, okay? Now what I'm going to do, I'm going to answer the question without any prior knowledge, and then I'm going to think, right? So using the periodic table as a guide, list the following order of increasing, right? So increasing means small to large, right? So what's the lowest? Sodium. What's the highest? Oxygen. Who's next lowest? Lithium. Who's next highest? Nitrogen. And that's what 99% of students write down, and those 99% of students are wrong. Are you shouting at the screen right now? These two are switched, aren't they? Okay, because they had that special arrangement, okay? So the answer is actually NaLiON. Boom. Small or large.
It's a trap!
It's rare they'll try and trick you like that, but occasionally they will. Okay. All right. Subsequent ionization energies. We talked about this already. I already mentioned it, but we'll draw it again. Okay, so that second ionization for sodium is super high, right? So sodium has up to 11 ionization energies. Second one, as we saw, is super high because here's my sodium. That's a plus 11 nucleus. If I've removed one electron, it looks like neon. We saw that earlier, right? So there's sodium plus 1. Okay. And then when I try and turn it into sodium plus 2, I've got to pull like one of those valence out of there, right? And that's really hard to do because of the plus 9 effective nuclear charge. Oh, that's gone. There we go. That's not there anymore, right? Plus an electron. And that is 4,560. It's, what did we say? 300 and something before. So it's more than 10 times harder to break into that second layer underneath, okay? So that's super hard. So look, there's our first ionization, 400. There's our second, 4560, yeah? Okay, and then it takes a similar amount of energy to remove these remaining ones, and then we try and break into that inner, and it's even harder, right? Okay, so what we see is something interesting. Okay, if we think about it, column one electron on the outside, that's easy to go, right? And then the rest are hard. So we see for sodium, the first ionization is super easy, and the rest are really hard, right? Magnesium, 2 on the outside, group 2. The first 2 are easy, and then we got that inner core left, and the rest are hard. So we see this step function, right? It's easy to get out the valence electrons, and then once you get that underlying core, suddenly you hit a brick wall, essentially, right? So aluminum, to get the first 3 out, silicon, the first 4, etc. So, you see as many as there are in the valence layer that are easy, and then you hit the core and it's hard, okay? And we see that kind of here for magnesium, there's 2 easy ones and a hard one. There we go. Okay, so that's subsequent ionization energies. Okay. Now, electron affinity. If ionization is the energy it costs to get one out, electron affinity is the energy I get back when I put one in. Okay, so it's the reverse process, if you like, right? So what's electron affinity? Electron affinity is the energy released when an electron adds an electron. Sorry, let me rephrase that. Electron affinity is the energy released when an atom gains an electron. If you remember, like the reverse process, so I pulled an electron off, it costs me energy, I put it back on, I get energy back, okay? So, for example, chlorine, as we know, is electronegative. It wants to gain electrons, yeah? So its electron affinity will be high, right? So here we have chlorine. If we think about chlorine a second, it's column 7, so it has an effective nuclear charge of +7, right? So imagine, oh, that's, chlorine is one more layer, my mistake, right? There's my empty spot, right? So chlorine has an effective nuclear charge of +7 and an empty spot right there. So that electron can just come and sit in there. And when it does so, it fills that layer, it's attractive, you get a release of energy. Well, you get release of energy for 349 kilojoules per mole. Okay. Now, if you think about it, the more electronegative the atom, the higher its effective nuclear charge, in effect, right? So the higher the effective nuclear charge, the stronger it attracts electrons. So the trend's going to be somewhat like the trend in electronegativity, right? So it's going to be low down here and high up here. If you notice, and here's the graph. Now, we don't usually ask questions about electron affinity because there's so many exceptions. If you think about it, it's more of a chemical trend. It has more in common with electronegativity than anything else, because just like with electronegativity, the noble gases have 0, right? Because they have full outer layers, there are no spaces for electrons to go into, right? But fluorine is super high, as are the other halogens, because they have a high effective nuclear charge and a space. As we move further to the left and further to the bottom, the effective nuclear charge decreases because you're further to the left, right? And as you go down, the radius is bigger. So as we go down towards the bottom left, the numbers gradually decrease, they're less attractive, and we see the smaller numbers in the bottom left as we expect. Okay. Now we do see a couple of odd ones. Again, beryllium and nitrogen are essentially 0. So nitrogen, remember, has that half full subshell, so it has empty spaces, but it doesn't want to spin pair electrons like oxygen, right? So it's not going to pick them up willingly, so to speak, okay? So nitrogen is 0 for similar reasons we talked about with nitrogen-oxygen pair, right? And so is beryllium. Beryllium has that, 1s2, 2s2 configuration, so it has that full 2s subshell. It's not going to, effective nuclear charge is kind of small, okay? So again, that's why they're 0. So these are 0 for reasons we kind of understand. Okay, so we don't ask too many questions on electron affinity, but be familiar with the concept. Okay. All right. Okay, I'm feeling generous, right? We don't really ask questions on this, but print this page out, draw the electronic configurations of these things, and then tell me just in words why they have like negligible 0 electron affinities. Email. Okay. Now, trends. This is an old exam question. Real easy. Right? Okay. So, we don't generally ask questions about effective nuclear charge because, it's a little bit beyond the scope of the course. I was a bit enthusiastic in my first semester teaching, right? So, don't ask that one. All right, but so let's just excuse me a second. Oh, still good. I think I'm running out of time, but I'm okay. All right, so we're going to do increasing radius and decreasing first ionization, and these are the atoms. So no tricks, just three simple ones. You got lithium, potassium, and neon. All right. Now then, when I talk about radius, that's the largest, that's the smallest, right? So radius, smallest first, right? Smallest is neon, then lithium, then potassium. Okay. Decreasing ionization, largest first. So what's the largest? If I do ionization, the highest is top right, so that's the largest, that's the smallest. It's the same trend. Okay, so I've picked opposite trends and then reversed the question. Okay, that's kind of a common thing. So hopefully that makes sense. You got that one. All right. So my screen just ran out just in time. So stop there. Hopefully that makes sense. Any questions in the discussion? I'll see you next time.